Golf, a club and ball sport in which players use several clubs to hit balls into a series of holes on a course in as few strokes as possible. One of these strokes is named putt, and it is defined as a light golf stroke made on the putting green in an effort to place the ball into the hole. A numerous type of conditions can affect putting, from the length of the grass to the movement of the club. Nevertheless, we will be focusing on four specific design factors: the length of the putt, type of putter, break of putt and slope of putt. To understand these factors, we need to know which levels will be taken in each factor and understand its meaning. Starting by the length of the putt, it will be measured in feet and can be either 10 or 30 feet away from the cup. Type of putter: mallet or cavity back. Essentially, one have a larger club head aiding with the aim of the shot. Then we mention the break of putt. This refers to the curve the ball will take along its trajectory, which can take the value of straight or breaking, in case the ball needs to curve in order to reach the cup. And finally, the slope of putt, which can be level or downhill. Now that we understand these basic concepts, we can immerse in the problem number 6.20, which says the following. An experiment was conducted to study the effects of four factors on putting accuracy. The response variable is distance from the ball to the center of the cup after the ball comes to rest. One golfer performed the experiment. A 2 to the 4 factorial design with 7 replicates was used, and all putts were made in random order. The results are as follows. So we're going to solve this problem by using Excel. First, we are asked to find which factors are significant for putting accuracy. Then we are asked to tell by the residuals if there is any model inadequacy. So here are our four factors and its high and low levels. We are going to start doing the half normality plot. For this, we're going to start by having all the totals of each run with the sum of all the replicates of each row. And we're going to do 4 columns of sums and subtractions. This is our standard order. We're going to start with A, then double the signs of A. In C, we're going to double the signs of B, and in D, we're going to double the signs of C. So we're going to have as many columns, as many factors we have, and in the 5th row, there are no sum and no subtractions, but we're going to calculate the effects with our contrast, that is the 4th line. So after we have the effects, we're going to sort them by ascending order and give them a place and a location. With this, we're going to plot our effects by location. So this is going to be, because it's a half normal probability plot, it's going to be from 0 to 1. And here we can see that factor A and B are significant for location. So in order to prove this, we're going to do an ANOVA with the sum squares, the degrees of freedom, F statistic parameters, and the F from tables. From these, we can see that factor A and B are significant, so it's in accordance with our half normality plot. So we can do the residuals, and after that we can also see the dispersion test to find who is important for dispersion and to do our finals recommendation and check our model. So we're going to have the residuals. The formula is observed minus expected. Observed data, it's our collect data from the experiments, this table, and the expected it's going to be the solved equation according to the signs of each factor. So these are the signs of factor A, these of factor B, factor C, and factor D. So here it's our table of residuals by subtracting observed minus expected from the equations, from the solved equations, And here we are going to sort them by ascending order too, and we're going to give them a place and a probability. So here it's our normal plot of residuals. It looks okay. We also can plot the predicted yields versus the residuals. And each residual versus each factor, as you can see. So once we have the residuals, we can do the dispersion test. The dispersion test have a new variable that is f. F is calculated in base of the variance of the residuals of each factors in low level and high level. Here we can see it. And f is the logarithm of the variance of the factor in low divided by the variance of the factor in, the variance of the factor in high divided by the variance of the factor in low. So we're going to have as many factors and interactions that as f parameters. So we can plot f, and it's the same. We're going to sort them by ascending order with its name. This is a custom sort, and we're going to give them a place and a probability. So here we can see that only factor A is significant for dispersion. Also, the interaction between A and C affects. So here is why we cannot cut our design but from C, but from D we can. So D affects no dispersion and no location. So because A is significant for dispersion, we can plot them against our residuals to see in which level it's more accurate. Here we found that A in the low level is the optimum. So the other factors, we are going to take the average in high and the average in low to see where the distance is smallest. So smaller, sorry. So here is the average of B in high and of B in low, and the best is when we have the high level. The average of C, and it's in high, and D it's also in high. It's where the distance is smaller. So in conclusion, we can say that the best is going to be when we have factor A in low. In terms of natural language, it's in 10 feet, in cavity back, in braking, and in downhill. And we can say from the residuals that our model is accurate. I personally thought and considered resolving this exercise because it is a great way to understand that our course can be applied in any daily topic. In this case, improving one single goal stroke can improve a player's level, closing the gap and chances of winning a championship.